now, and then I will post the recording up online
Hughes, I have a
on the
question.
YouTube page. Yeah, go ahead.
So on the WebAssign homework, some of those questions, the numbers are pretty gnarly. And like I used a calculator. Are the numbers going to be that intense on the test? And should I learn how to do that without a calculator?
What do you mean by gnarly?
Like they're just like really big and square roots and just kind of like not very pretty to work with.
Yeah, so there will always be square roots when you're doing things like singular value decomposition, or at least 90% of the time there will be square roots because you have to just normalize things. So there will be some square roots. I think whenever we write exam questions, we usually try and make it so that they work out fairly well. So I would I can't swipe. There we go. Yeah, so I wouldn't expect terrible numbers, but there will definitely be radicals because that's just kind of how these problems end up working out all the time.
All right, that's
Is that
good
okay?
to know. Yep, thank you.
Yep. Okay, so the final exam will open on Friday. It'll open at like 12:01 a.m. on Friday. So first thing in the morning, you could take it. It'll be open for the duration of the exam week. And so I think exam week ends on Wednesday of next week, I believe. I forget if it's Wednesday or Thursday. So you should double check that, but it'll be open basically for the entire exam week. It's on WebAssign again, so it'll look a lot like the second midterm. When you open it up, from the minute that you open it up for the first time, you'll have 5 hours to complete it. So make sure that you're kind of prepared to kind of do it in one setting. Don't kind of open it up to, and then plan to take a break halfway through, because if you do, then the break will include the time that you have. So the break will lead up some of the time you have. So kind of make sure you're ready to sit down and do it. Let's see, what else was I going to say? If you start at kind of like 11:30 the night that it's supposed to close, you won't get 5 hours. You'll only get enough time sort of during exam. Like when the exam closes, even if you have time left on your personal clock, your exam will be done. So it'll look a lot like the other midterm. The questions will be formatted similar. So you've had a bit of experience with that. Now I see there's a few questions that seem to be coming up on the chat. I don't know if I can pull up the chat window. I don't know if that will be visible. I don't want to pull up the chat window because then your names will be. Yeah.
I can just read them out loud if you want.
Yeah. Would someone read them out loud? Or if you have questions, just don't worry about using the chat window. Just feel free to jump in. So yeah, if someone could read them out loud to me, that'd be great.
So the first one was, is there going to be any kind of curve in this class?
Yeah, so typically what happens is I don't curve the individual assignments or anything like that. What I do is at the end of the class, I add all the weighted scores up and you get sort of a weighted average. And then once I have a weighted average, then I will sort of determine the cutoff. So I'll kind of decide what's an A, what's a B, and so on. Typically, I won't ever bump the cutoffs up. So I won't ever make it harder to get an A or harder to get a B or whatever. I will, typically I'll bump the cutoffs down a percentage or two. In Math 313, the grades typically were a little bit lower, so I would curve it. I'd sort of bump the cutoffs more. Judging from how people did last semester, the grades were generally a bit higher, so I did a little bit less curving, but there will probably be some adjustment of the cutoffs. Other questions in the chat?
The other question was, how long should we expect the exam to really take?
Yeah, so everyone's going to be different on that. For those, you have a full extra hour compared to the second midterm. It shouldn't be that much longer than the second midterm, maybe like 10% longer. That's always a little bit hard to judge on our end, but it shouldn't be too much. It shouldn't be too much longer than the second midterm. So if you found that you had enough time on the second midterm, then I would certainly think you would be okay on the final two. Other questions?
That's all the ones in the chat.
Okay, cool.
I got one more.
Yeah, go ahead.
With your earlier classes today, did you review like different stuff and then you're recording this one? You recorded all three, or are you just recording one?
No, I'm recording all three. So the only difference is we'll go through these final exam review slides right here. We'll go through them all right now. And I did that in each section. So you'll all see that. So that'll be common to all of them. then but then the questions that I pull from the exam that we're going to do after that, those will all be different. So you might want to just like skip over the beginning part and watch the other ones because there'll be different material each time. I will also hold a review on Thursday morning. I haven't quite decided exactly the time for that. I won't hold 3 separate reviews. That's reading days, so hopefully everyone's schedules are opened up a bit more. But I'll pick just kind of a window in the morning and do some more example questions then. And then the math lab is holding 2 reviews as well later on Thursday afternoon and Thursday evening. So hopefully on Thursday there'll be a lot of opportunity for you to review. Any other questions about the format of the exam? Anything else before we start actually reviewing?
Is the exam going to be like cumulative? So should we expect like questions from like the other exams to be on there?
Yeah, so it will be cumulative, although it'll be weighted towards sort of the end material in the class. Now, we won't ask you a lot of direct questions from the earlier chapters, but the thing is that the material, in order to do a question about singular value decomposition, you need to know something about, like there's the sort of the material in the later section really builds on the material in the earlier section. So even though we might not ask you a direct question about something in an earlier section, it will still probably show up just in how it's related to the later stuff. But it is cumulative. We will ask a few questions from earlier sections, so it will be weighted towards the later stuff. Other questions? Yep. No. All right. Well, let's get started then. So this is just a little bit of a disclaimer, mostly meant as a joke. The reason I put it there is because, this is sort of not the one I wanted, actually. I'm sorry. Let me upload the one I want. The disclaimer there is kind of a joke, but really what it's doing is I'm always a little hesitant to create sort of a list of topics to study because there's I might not include a topic on the list, or maybe there's a topic on the list that I sort of consider as being a part of a different topic that is listed, and maybe some student's going to see that, this thing doesn't show up on the list, I don't have to study it. This disclaimer here is just saying just because it doesn't show up on the list doesn't mean you don't have to study it, but this list should give you a broad outline of things you need to know. So chapter 1 is all that early stuff we saw, and most of this stuff kind of comes up later in the class. So you probably won't need to go and study too much from chapter 1 directly. It covers vectors, dot products, orthogonality, and like norms, lengths of vectors. So those things will be kind of, show up in a lot of different places. So chapter 2 is where we really kind of jump into things. We cover systems of linear equations. Now, if we give you a system of linear equations, there's kind of 2 key questions you might want to ask. The first question is, does this system of equations have a solution? And the second question is, if it does have a solution, will that solution be unique? Okay. So how do you tell whether your system of equations has a solution? And if it does have a solution, how do you tell whether that solution is unique? Or is it possible that there's infinitely many solutions to your system? The way that we study systems of equations is we try and simplify them using row operations and row equivalents. So this is kind of the row reduction algorithm. We talked about linear combinations of vectors. So for example, if I give you a vector y, okay, so suppose you have a vector y, and suppose that you can write down the vector y as some sort of c1 times v1 plus c2 times v2, and so on. Okay, if you can express your vector y as a combination of these vectors with different coefficients on them, then we say that y is a linear combination of the v vectors, okay? And so once you understand linear combinations, you can start talking about spans. So the set of all linear combinations is called the span of the vectors. And we can ask, when do vectors span Rn? You can also, another way to think about linear independence, or sorry, linear combinations is in terms of linear independence. And one of the things you should be prepared to answer is, or prepared to be able to answer is to determine whether a given set of linear of vectors is linearly independent. Okay. So any questions kind of on the chapter 1, chapter 2 stuff?
Could you give the definition of orthogonality?
So orthogonal vectors, yeah. So orthogonal vectors are just two vectors u and v are orthogonal if their dot product is equal to 0. Okay, and so you should think of this as basically telling you that these two vectors are 90 degrees from each other. So that's what it means for two vectors to be orthogonal. Is that okay?
Yeah, that's good. Would it also be okay to say like they're perpendicular, or is that like?
Yeah, I mean, you got the right idea in mind. I think the reason we don't say, yeah, more or less, perpendicular and orthogonal mean the same thing. The reason we don't say perpendicular is because, well, I mean, what does it mean for two vectors in R15, in like say R7 to be perpendicular? It's harder to, you can't really picture vectors in higher dimensions. And so kind of the idea of what we have in mind for two things being perpendicular kind of breaks down in higher dimensions, but it's really the same thing. It's just, we call it orthogonal in this class is really the only difference. So other questions? All right. So then we get to chapter 3. We see matrices. We learn about inverses of matrices, or matrix inverses. So the first thing you should be able to do with a matrix is if you should know how to find the inverse of a matrix if such inverse exists. And then you should also know a few properties of inverses. So for example, if I have, say, A times B, and these are both invertible matrices, well, I can multiply them together and then take the inverse. But this is the same thing as taking the inverse of B and multiplying it by the inverse of A, okay? Where I've kind of swapped the order, okay? So this is like one property of matrix inverses you should know. And there's others. I'm not going to list them all, but for example, if you want to take the inverse of the transpose of a matrix, that's the same thing as taking the inverse and then taking the transpose, okay? So there's other properties, but this is kind of what I mean when I say properties of inverses. We learned about the invertible matrix theorem. And remember, this is the theorem that kind of shows up in a bunch of different parts. And these parts are essentially all telling you about ways in which you can determine whether a matrix is invertible or not. So if you have a square matrix, one way you can tell if it's invertible or not is whether it has 0 as an eigenvalue, or whether the null space is equal to just the 0 vector, or whether the columns are linearly independent, or whether the rows span Rn, or whether, there's all these different things that allow you to conclude that a matrix is invertible. And so what you should, I wouldn't suggest that you go through and like memorize every single part, but you should be able to sort of go through and say, well, hey, if I know that 0 is an eigenvalue, then I know that the null space has to be non-trivial, and therefore the equation ax equals 0 has a non-trivial. So, you should kind of be able to go from one part to the other and kind of know why they tell you something about the matrix being invertible. So so don't memorize like part 1, 2, 3, 4, 5, 6, 7, and so on, but you should be able to sort of recognize those things when they come up, and you should be able to kind of jump from one to the other and kind of understand why they're equivalent. Any questions there?
Real quick, can you tell me why 0 as an eigenvalue is relevant to invertible matrices?
Sure. Okay, good question. So if 0 is an eigenvalue, that means that there is a non-zero vector x that satisfies that equation. Are you okay with that?
Yes, sir.
Okay, so when we multiply the scalar 0 times the vector 0, that just gives us the 0 vector on this side. Okay, so if 0 is an eigenvalue, it tells us that there, and again, every eigenvector has to be non-zero, right? So the eigenvectors have to be non-zero. So if 0 is an eigenvalue, then that means there's a non-zero vector x that satisfies this equation. But if there's a non-zero vector x that satisfies this equation, then, I mean, there's a lot of things you could kind of observe there. I mean, for one, it means that the matrix has free variables. It doesn't have a pivot in every column. It tells you that when you row reduce this matrix, it's not going to give you the identity matrix. And that's also something that would have to be true if our matrix is invertible, and so on. So whenever you have a non-trivial solution to an equation like this, you know that your matrix cannot be invertible. Is that enough there?
Yes, it is. Thank you.
Convinced you? All right, no problem. All right. So then we talked about subspaces. There's that definition or that way of determining whether a set is a subspace. There are a few examples of subspaces we saw. We saw the row space, the column space, and the null space of a matrix. We learned about bases. So remember, a basis is a set of vectors that's linearly independent and which spans the subspace. And we saw that, you know, we have these examples, row space, column space, and null spaces. And we learned that for each of these, there's a procedure to finding a basis for each of these, okay? So we could ask you to find a basis for any of these things. Now, sometimes we might ask you to find a basis for something that's not a row space or a column space or a null space. And in that situation, remember what we did is, for example, if we give you a bunch of vectors and ask you to find a basis for the space they span, the trick we typically do is we try and write those vectors, we try and write them as the rows of a matrix, and then all of a sudden the space that we care about is the row space of a matrix. So even though not every subspace we see is an example of these three things, is an example of one of these three things, oftentimes we'll give you problems where you can convert it into a question about a row space or a column space. We talked about the dimension of a subspace. That's just the number of vectors in a basis. Is there a question? Thought I heard someone. Just in my office alone talking to a screen, so I have no idea if, yeah, I don't know if anyone asked a question.
Actually, I do have a question, Dr.
Yeah.
Hughes.
Go ahead.
So the difference between a subspace and a basis is that, like, to find row and column spaces, we row reduce the matrix and find like non-zero like rows and then like what pivot columns are. And then do we take the original rows and columns that correspond to that for subspaces, but then for bases, we leave it row reduced? I get confused on when we leave it the same and we go back to the original.
Yeah, so your question is kind of different than, so you're on the one hand, you're kind of asking about what's the difference between a basis and a subspace. And then on the other hand, I think you're asking kind of about how do you find a basis for the row space or column space? How do you know whether you go back to the original matrix? How do you know whether you stay with the reduced one? Is that kind of,
Yeah, exactly.
It seems to me you're asking two different questions. Okay.
Yeah, sorry, but that's the basics of what I'm asking you.
I'll try and answer both questions then, okay? So the first is, what's the difference between a basis and a subspace? Okay, so for example, let me just draw a simple example. So suppose that we're in R2, okay? If I draw a line, a straight line that passes through the origin, this line here is a subspace. Okay, and so this line really consists of infinitely many different points. Okay, every single point on this line is a vector in the subspace L. Okay, so the subspace is the entire line. Okay, on the other hand, if I didn't want to like write out the equation of a line, I could just give you a single vector that lives on the line, and this single vector, I'll call it V. Okay, notice that any other vector on the line can be written as, say, some scalar times V. So for example, if I wanted to look at like this vector here might be 2 times V. And this vector here might be -1 times V. And this vector down here might be -2 times V. So every single vector on the line or every single vector in the subspace can be written as some linear combination or some scalar multiple of V. So V is the basis, okay? V is the basis, whereas L, the line, is the subspace. So in general, subspaces have infinitely many points, and they always look like a line or a plane or something like that. Whereas a basis is just like 1, 2, or 3 or whatever, some finite set of vectors you can write down. And these vectors allow you to sort of build anything in the subspace using linear combinations of them. Does that help with the first question?
Yes, for sure. Thank you.
Okay, so yeah, so the bases are like your ingredients, right? Like I have eggs, milk, flour, water, and yeast. That's my basis. But then using those ingredients, I can cook up an infinite number of recipes, and the collection of all those recipes is the subspace. So back now to the second question is, you know, if I give you a matrix, you know, I'm just going to write down a random example here, and I'm not actually going to row reduce it. Something like this, right? If I were to kind of row reduce it down, and suppose I got something like this, okay? Well, if I'm interested in the row space, okay, if I'm interested in the row space first, what I'm going to do to find a basis is I'm just going to take the non-zero rows, okay? So I'm going to take that row, and I'm going to take that row, and that'll give me a basis for the row space. Okay, so I take the non-zero rows of the reduced matrix, okay? On the other hand, if I want to find a basis for the column space, what I have to do is I figure out where the pivot columns are. So in this case, I have a pivot in the first and the second column. But then what I do is I go to the original matrix and I pull out the corresponding columns, okay? So for the row space, you find your basis by taking the vectors from the reduced version, whereas the column space, you go back to the original version. Does that answer that part? Yeah.
You could, for the row space, go back and take the original rows from the original as well. It would still be a subspace basis, right?
Well, yes, if you're careful, okay. And the reason you have to be a little bit careful is because during row reduction, if you swapped the position of two rows, that might mess something up, right? So if you sort of kept track of where every row came from, you could go back and sort of take the corresponding rows. But if you did a bunch of row swaps, then the first and the second row over here might not have come from the first and the second row over there originally. Does that make sense?
Yep.
Yeah. So you just have to be a little bit careful, but you're right. Yeah. All right. Any other questions before we move on? No? All right. So we also talked about coordinate vectors. Remember, if you have, say, a basis B, so suppose you have some basis B1, B2, and so, you know, then if I take a vector Y, maybe I can write down Y as like 3 times B1 plus 7 times B2. Okay. Well, there's if this here is a basis, then there's really only one set of coefficients that's going to allow me to express the vector Y as a linear combination. So what I can do is I can take those coefficients, and if I put those two coefficients in a vector, this vector here is the coordinate vector of Y with respect to B, the basis B. Okay. Let me just do one thing. Okay. So any other questions there? No? All right. So we also learned about the rank theorem. We talked about linear transformations. We talked about showing whether a transformation is linear or not. We learned how to find the standard matrix of a linear transformation. And we saw a couple different kinds of examples. So there were some examples where we gave you the formula for the transformation and you had to find the matrix. In some examples, we gave you like the geometric description of the transformation and you had to find the matrix. But that about did it for chapter 3. Any other questions there? Nope. All right. So chapter 4 is where we started eigenvalues and eigenvectors. So we saw eigenvalues and eigenvectors. Now remember, there's an algebraic definition involved here. So you know, an eigenvector is a vector that satisfies this equation, a non-zero vector that satisfies this equation for some scalar. But we also have sort of a geometric way to think about eigenvalues and eigenvectors. And remember, those are eigenvectors are vectors where when they get multiplied by the matrix, they don't get rotated or spun or anything. What happens is they just get rescaled. Okay? So you should sort of have the algebraic definition sort of understood, but you should also sort of have this geometric picture in mind. All right. Then we talked about eigenspaces. So remember, if you take, you know, if you take all the eigenvectors that correspond to an eigenvalue, so say, you know, say you have lambda 1 equals 2, lambda 2 equals 2, and suppose you get like a v1 and a v2 here for these eigenvalues, then these two vectors, suppose they span like a plane here. Okay, well, if these two vectors are eigenvalues for lambda equals 2, eigenvectors for lambda equals 2, then the plane that they span, that would be called the eigenspace. And so whenever you pick a non-zero vector out of an eigenspace, that vector is going to be an eigenvalue, or an eigenvector, I should say, okay? So oftentimes what we'll do is we'll ask you to find a basis for an eigenspace, and that really just corresponds to finding linearly independent eigenvectors inside of it. Questions there? Okay, so we talked about determinants, we talked about computing determinants, also properties of determinants. So for example, if I give you determinant of A transpose B inverse, well, you should remember that that's the same thing as the determinant of A transpose times the determinant of B inverse. And the determinant of A transpose is the same as the determinant of A. The determinant of B inverse is 1 over the determinant of B. So we definitely could give you a question like this where we ask you, where you have to kind of know some properties of determinants in order to kind of simplify things. We talked about characteristic polynomials, similarity of matrices, and then the big thing was we talked about diagonalization. Now, remember, the question of telling whether a matrix is diagonalizable or not, it takes a little bit of work. So for example, if I have a matrix and the eigenvalues are, say, lambda 1 is 2, lambda 2 is 2, and say lambda 3 is 5, okay? Well then, because this eigenvalue shows up twice, I would say that the algebraic multiplicity is equal to 2, okay? Because it shows up twice. Now, when I go about looking for eigenvectors, I might get 2 eigenvectors out of this. I might get 2 linearly independent eigenvectors, okay? Now, if I find 2 linearly independent eigenvectors, then I would say that the geometric multiplicity is equal to 2, okay? Now, in this case, if the algebraic multiplicity equals the geometric multiplicity, that's good news if you're trying to diagonalize your matrix, okay? And if it turns out that the algebraic multiplicity and the geometric multiplicity matches for every eigenvalue, then you can diagonalize your matrix, okay? The problem comes in if you only get 1 linearly independent eigenvector in a situation like this, okay? In this case, if I only got 1 linearly independent eigenvector, then my geometric multiplicity is only equal to 1, and since it's smaller than my algebraic multiplicity, I'm not going to be able to diagonalize my matrix, okay? So I might as well stop at that point there, okay? So the geometric multiplicity and algebraic multiplicity are important because they kind of tell us when we can diagonalize our matrix and when we can't. Any questions on that? No? All right, well, we'll keep rolling then. Chapter 5 is where we learned about orthogonal sets of vectors, orthogonal matrices. Remember, orthogonal matrices are square matrices with orthonormal columns. And so orthogonal matrices have a lot of nice properties. For example, if U is orthogonal, then the transpose is just equal to the inverse. We also know that the determinant of an orthogonal matrix is always plus or minus 1. We know that eigenvalues of an orthogonal matrix are always equal to 1 in absolute value, and so on. So there's a lot of nice properties about orthogonal matrices that we saw. We talked about orthogonal complements. So remember, that was this picture here. You know, you've got some plane W, and W perp in this case would just be a line. So any vector inside of W is orthogonal to any vector inside of W perp. That's kind of what makes them orthogonal to each other. We talked about orthogonal complements of row spaces and column spaces. We talked about orthogonal decomposition. So I can always take a vector Y and I can split it up into a piece that's parallel to W and a piece that's perpendicular to W. We talked about the Gram-Schmidt procedure, which takes an orthogonal set of vector, which takes a basis, which might not be orthogonal, and converts it into an orthogonal basis. We talked about orthogonal diagonalization. Now, remember, if you want to know whether a matrix is orthogonally diagonalizable, you don't have to check. If you care about regular diagonalization, then remember you have to check the algebraic and the geometric multiplicity. But if you just care about whether it's orthogonally diagonalizable, there's a lot less work you have to do. The only thing you have to do is check whether A transpose is equal to A, okay? And so if your matrix is symmetric, then your matrix will be orthogonally diagonalizable, and vice versa, okay? And that's basically the content of the spectral theorem. Basically, if your matrix is orthogonally diagonalizable, then it's symmetric and vice versa. And then we saw things like the spectral decomposition, and then we got into kind of chapter 7 where we saw the singular value decomposition and learned about things like singular values. So this is kind of a good summary. I think if you are fairly confident with all of these things, then you should be fairly confident going into the exam. That, I mean, each of these topics kind of contains sort of smaller subtopics, and so definitely, you know, you should sort of understand these probably pretty well. But you know, and just because a topic didn't get listed here explicitly doesn't mean that it's not sort of part of another topic. So, but this should give you a good idea of what to be looking out for when you're studying. Any questions on this?
Yeah. So, Dr. Hughes, this is like a lot to study, and so what do you recommend, like, or how do you recommend that we study for this? Because, you know, a lot of these topics, they have like equations kind of that we have to know about, and along with like the processes of doing it. So yeah, what is like the best way that you recommend that we study?
Well, everyone's going to study a little differently. Some, you know, I've had students in the past who make up cue cards, or like not cue cards, but note cards, and will like index cards will just like, you know, I had one student who just had a huge stack of index cards she carried around all semester. That's not going to be everyone's style. For me, when I sort of was preparing for an exam, typically what I found most helpful was to just do as many practice problems as I could. And so, because you're right, not every, I mean, some topics will kind of show up again and again, and some topics are sort of, you know, more likely to show up on the test, perhaps, just because they kind of make for good test questions. So if you know, I would take the practice final. I definitely work through that. Then I'd work through some of the older practice finals and stuff like that. You can also work through the older midterms and the older practice finals. I mean, I think for each midterm, I posted a practice midterm plus the old midterm plus the old practice midterm. And now you also have the old midterm as well. And so for each midterm, I think you have 4 different exams you could go through. And then for the final, you have 3 different ones. There's probably enough multiple choice questions that you could keep pretty busy just working through those for a while. And so I would probably do that. And then just as I come across one where I get it wrong, I would just make a note of what topic it was about, and I'd make a note of the question, and I'd sort of build up a study sheet based on the ones that I'm getting wrong, and then kind of go from there, and let that kind of guide your studying. But everyone's going to learn a little different, so that's maybe how I would do it. But I you know, everyone's going to have a different technique that works for them. So does that answer your question?
Yeah, those are some good ideas. Thank you.
Yeah, I mean, not everyone's a bit different, but hopefully something like that will work for at least a few of you. Other questions? No? All right. Well, let's go to the practice, or not the practice final. We're going to go to the final exam from last semester, okay? Now, as you can see, we did a few questions in the previous classes. If you want to go look at what we talked about there, you can always go online and you can look at the videos I've posted already. We're going to kind of continue on and do some more questions here, okay? So let's start with example 5 here. So this is from the midterm or the final exam from last semester.
Dr. Hughes, are you talking?
Did his mic cut out?
Dr. Hughes, we can't hear you.
Can anyone even see a screen?
It looks like your mic is muted, Dr. Hughes.
Are y'all's screens frozen too? Oh, he said that.
Hey, can you guys hear me?
Yes.
Yeah.
You can hear me now. Okay, how long was I gone for?
A minute.
Really? Okay.
We didn't even see the beginning of the problem 5.
Okay. All right. Well, let's go back then. Let's see. So I can see it now. All right. Okay. I think we're can you all see that? The problem 5?
You're good.
Okay. All right. So we have a 5x7 matrix. I like to kind of just write down what the matrix kind of looks like. And I haven't really done anything but sort of depict the fact that it's kind of a short, wide matrix. I'm told that the matrix is rank 4. What does the rank of the matrix tell me in this situation here?
It tells you how many linearly independent rows there are.
Yeah, linearly independent rows or linearly independent columns is another way to look at it. Or you can just think of it as those are two good ways to look at it. You can also just think of it as the number of pivots you have. So if it's a 5x7 matrix and it's ranked 4, that means I'm going to have 4 pivots, and I don't know exactly where they'll be, but I'm just going to kind of write them out like this. So you know my matrix kind of looks like this, and then I have another row of all zeros. That's just a kind of, you know, I have no idea what happens sort of in these spots. Just one second here. Hello? Hello? Okay, no idea what that was. I never get calls here. Anyways, so I don't know what's going to go in these spots, and it doesn't really matter. But I just want to write down that I have these pivots here just so I can kind of keep track of what's going on. So what is the dimension of the null space? Oh, this is actually kind of easier than I didn't really need to do all that work. We're asked to find the dimension of the null space. So remember, this is we have the rank theorem, and the rank theorem tells me that the rank of a matrix plus the dimension of the null space of that matrix has to be equal to the number of columns. So in this case, I have 7 columns, and I'm told that my rank is equal to 4. So what does that tell me? The dimension of my null space has to be, well, it has to be 3. Okay? So I actually didn't need to do all this. I should have read the question fully before I did any of this. But so in this case, we're told the rank of the matrix. We know it has 7 columns. We know that this formula has to hold, and so we can find the dimension of the null space. What's another word for the dimension of the null space?
The nullity.
Yeah, the nullity of the matrix, okay? So we could have asked you to find the dimension of the null space, or we could have asked you to find the nullity, and both are the same thing. I don't think 6 is that important, so I'm going to skip it. It's kind of just a random question that showed up once upon a time, but it probably won't show up again. Questions?
And if it does show up, what do we do?
If it does show up, then you just continue on a wing and a prayer. There's not much you can do. I mean, it's not that hard, but it's just a random question that is not going to show up. So don't worry about it. So let's look. Problem 7 is more like a standard type question that you might expect to see. Okay. So this is asking us, we have a linear transformation from R2 to R2, okay? And it rotates vectors x counterclockwise by pi over 2 radians, okay? So this is sort of the linear transformation that takes vectors, say it takes this vector here, and it's going to rotate it 90 degrees, okay? We want to find the standard matrix for this transformation. All right, so how would we do that? How do you find the standard matrix? Can anyone remind me what the standard matrix of a transformation, how you find that?
You use the identity vectors, right? Like 1, 0, and 0, 1.
Yeah, exactly. So the first column of this matrix here is just going to be given by whatever vector I get when I plug in 1, 0 into the linear transformation. Okay, so I just want to move that over a bit. So yeah, so the first column is just whatever I get when I plug 1, 0 in. The second column is just whatever I get when I plug 0, 1 in. Okay, so let's go ahead and let's find that. So if I look at my vectors here, so here's the vector 0, 1. Okay, when I rotate it 90 degrees, I'm going to end up with the vector, or sorry, that's 1, 0. When I rotate it 90 degrees, I get 0, 1. And so that tells me then that my first column is 0, 1, okay? Because that's what happened to the vector 1, 0 when I plugged it into the transformation T. Now I can do the exact same thing, but now starting with the vector 1, 0. And when I rotate the vector 1, 0, I end up with the vector -1, 0. And so that becomes my second column, -1, 0. Okay. Any questions there? So it's always these vectors we plug in, okay? It's never, so sometimes people ask, well, how did you know to plug in 1, 0 and 0, 1? You always just plug in these standard basis vectors. If it was a linear transformation from R3 to somewhere else, then I would have plugged in 1, 0, 0, 0, 1, 0, and 0, 0, 1. Sorry, that's messy, but okay. But that, I mean, so whenever you're looking for the standard matrix of a linear transformation, you always just plug in these special standard basis vectors, okay? And they give you the columns there. Questions on that? No. All right. So there's this one here is just kind of asking if you know this fact. If you have 3 matrices and you want to multiply them together, does it matter if you multiply B and C together first and then multiply A? Or is it the same thing as when you multiply A times B and then multiply C? It turns out you're going to get the same thing either way. And that property is called associativity, okay? I wouldn't be too worried about studying all these different names of properties and stuff like that. Remember, commutativity, if matrices are commutative, it means that when you multiply them, you can swap the order. That's what it means to be commutative. And then this property here is associative. But I wouldn't worry too much about all the other property names. They're not super important. So, any questions there? No, let's try and bang out one more question, okay? Let's see. Let me pick the best question. Yeah, let's do this one. Let's do number 10. I like this question better, okay? So let A be an invertible square matrix, okay? And suppose that it has eigenvalue lambda with corresponding eigenvector x. Which of the following must be true, okay? So let's go through this list here and let's try and pick out which of the following things have to be true, okay? So is the first one true? Can anyone tell me?
Yeah.
Yeah, and why does it have to be true? Well,
it's like the definition of the eigenvalue and eigenvector.
Yeah, exactly. It's just kind of by definition, okay? Second option, is it going to be true?
Yes.
Well, yeah, it is going to be true. Yeah. And the reason it's true is because you can just kind of take the first equation we see here, this first option. Because our matrix is invertible, we can multiply both sides of this equation by A inverse. And we're going to get A inverse times AX equals A inverse times lambda x. And if we kind of simplify what's here, we just get the identity matrix, so you just get x, and we can pull the lambda out. We get lambda A inverse x. And then because our matrix is invertible, we know that lambda can't be 0, so we can divide both sides by lambda, and we get this, okay? So essentially what this is telling me is it's telling me that if lambda is an eigenvalue of A with eigenvector x, then A inverse is also going to have x be one of its eigenvectors, but the eigenvalue is going to be 1 over lambda. So that's a true statement there. Okay? Everyone okay? The next one is the determinant of this matrix equals 0. Is that one true?
Yes.
Yeah, this is true, and this is essentially how you find the eigenvalues, right? Remember, the eigenvalues are precisely the scalars that satisfy this equation here, right? Because if the determinant of A minus lambda I is equal to 0, then that means that this equation here is not invertible, in which case there's going to be a non-zero solution to this equation. Anyways, scratch that last part. It's not super, probably hard to follow there. Okay, but remember, when we find the eigenvalues and eigenvectors, the way we find the eigenvalues is precisely by finding values of lambda that satisfy that. So that's true. What about option 4, x is equal to 0? Is that a possibility?
No.
What's that?
No.
Yeah, remember, eigenvectors are never 0. Okay, and that's by definition as well. So 0 is never an eigenvector, and therefore x can't be 0. The last one is asking if A minus lambda I is invertible, and that's also going to be false, because if A minus lambda I is invertible, that means that its determinant is not equal to 0, okay? And so if the determinant of this is not equal to 0, what does it tell me about lambda? Well, if that determinant is not equal to 0, then it really means that lambda isn't an eigenvalue. Okay. So really, we want this determinant to be equal to 0, in which case this matrix would not be invertible. Okay. And so that option is false there as well. All right. So that does it for time today. Any questions before we move on, or before we sign off here? Again, I will hold a review on Thursday morning, and instead of we won't go over the slides again, but what we'll do is we'll basically just jump into practice problems just like this, and we'll just work our way through old exams and stuff like that. So that's what we'll be doing.
Thursday will that be?
I haven't quite decided. I have some seminars, like virtual seminars, that I need to attend that day, and so I just wanted to double check my calendar but I'll send that out in an email with some other pertinent information. So any other questions before we sign off then? No?